Right. Morning, everyone. This is room 404. This is going to be the presentation on new developments in CEMS, analysis using quantum cascade laser spectroscopy, and Dave McMillen with Emerson Automation Systems, who is here to present for us.
Good morning. I'm Dave McMillen. I'm the business development manager for the quantum cascade laser and our traditional process gas analyzers as well. Been with Emerson for about 6 years. I came specifically for this particular technology. Emerson's been around since 1890. I don't go quite that far back to 1980s. And I was there for about 3 years, and I went into biotech for a while, and then I've been involved with process analyzers over the last 20 years, specifically focusing on laser-based analyzers. And so when I heard that, and we'll look at this, when I heard that the QCL product was purchased by Emerson, I came because it's a great product. And this is just a little bit. One thing is there's a lot about sustainability now in the market, and I have to say that Emerson's been doing this for a long time, based on if you go all the way back to the Beckman days with the analyzers that we did for CEMS. We've been doing this for a long, long time, and so. Getting ahead of myself. So what I'm going to talk to you about today is it's a newer technology. It's not that new, but it's certainly newer to a lot of people, and it's quantum cascade laser spectroscopy, specifically applied to CEMS. And what we're going to talk about a little bit about the history of the lasers themselves and using this in a variety of applications. I'm going to talk about why people are interested in QCL, what benefits it brings, and then how it applies to CEMS, both traditional cold-dry CEMS as well as hot-wet CEMS. And then with a little diversion into DeNOx because of the way that we're able to handle ammonia. And then just a bit about maintenance. So there's a lot here. I'm not going to get into everything, but the story with QCL starts before 2003, but the 2003 is when Cascade Technologies got started outside of Glasgow, Scotland. They saw the promise of the technology, but it was very raw and it wasn't process ready by any means. So what you see in this timeline is a march from 2003 all the way through up to the present time of making this into something that will work 24/7, 365, which is what you need for CEMS, which is what you need for process analyzers. And along the way, besides developing the technology to make sure that the lasers are very, very stable, they were used initially. The first application was CEMS on ships, measuring the emissions on the funnel of cruise ships and other ships as well. So that was the first start. They went on to doing work with looking at leak detection leak detection with aerosol cans as they're going through it 300 cans a minute, actually being able to find the hydrocarbon propellant leaking and then kick off the leaker within a meter. So it's a very interesting technology. It's very fast and reliable. Combustion control is one thing that we've done, as well as automotive emissions, so tailpipe emissions. So we've OEM'd our systems for some of the major automotive testing companies. Now, Emerson bought them in 2015, and of course, because we're interested in process analyzers, that's the direction the money funneled to that. So what we did was in 2016 introduced our line of this. It's a CT5000, which is our third generation process analyzers. And that's what you see on the right-hand side. That goes along with our standard analyzers, the traditional FTIRs, excuse me, NDIRs, paramagnetic, those standard technologies that we've had for many, many years. And we've added the quantum cascade laser to that now. And so what you'll see is there's a variety of, I won't talk about that. Mostly what I want to talk about is how these things work and why people are moving to this technology. Additionally, we can't talk about extractive CEMS systems without talking about a little bit about sample handling and protecting the analyzers. So that's an important part of CEMS, of course. And so you need that sort of capability. So I'm going to talk about capabilities in the theory. So what's the difference? I mean, you've got NDIR to measure CO, to measure CO2. You've got chemiluminescence to measure NOx. Why is there a difference, or what is the difference? And really, the difference is that laser technology allows you to get the light at the specific wavelength to excite the molecules you're interested in measuring, because we're doing this with absorption spectroscopy. Well, I'll get into that a little bit more. Additionally, being able to measure multiple things, multiple analytes within one analyzer is advantageous, and so we can put multiple lasers in there. The laser stability, as I mentioned, we did a lot of work to make them very stable. So they run 10 to 15 years, and that's critical for the reliability of the analyzers. Reliability is critical to CEMS. They can also operate at high temperatures. At least the analyzer is designed to operate at higher temperatures. And the combination of that the lasers are stable and that the areas of absorption are physical properties, that means that we have a very stable measurement. So we have no zero drift and we have very little span drift. There's also no moving parts. When you fire up one of our analyzers, it makes no noise. You know, there's no wheels, there's no fans, well, we do have a cooling fan in one of ours. I'll back up on that one. And then they're also fast. That's not necessarily an issue with CEMS, but it is with process analyzers. If you're looking for acetylene in an acetylene converter, speed is important. And then, like I mentioned, no moving parts. There's also no consumables. So we're not burning anything. It's not a flame analyzer. We don't have carrier gas, those sorts of things. These are, on the right-hand side, are the measurements that we make. And on the left-hand side, I just threw up some chemical and refinery applications that we do outside of CEMS, but we do a lot of CEMS, a lot of DNOx as well, looking at ammonia slip, as well as NOx after SCR. But things like looking at the off gas from the FCCU regen, looking at impurities in hydrogen, et cetera. So there's a number of different things that you see there outside of CEMS. But the measurements that you see, O2, CO, CO2, NOx, SO2, water, even HCl, HCN, HF, and ammonia, those things apply to emissions monitoring. So how does it work? What you see on the left-hand side is a cross-section of our optical bench. And right here are the laser modules. Then you've got your flow cell with mirrors on either end. And we direct the laser light. There's up to 6 laser modules up into, this is a Harriet cell, a stigmatic Harriet cell. And your sample comes in and out and bounce the light back and forth by a particular wavelength. Particular optical path length. And the longer the optical path length, the more sensitive the image. So we have a variety of different light itself exits to the detector itself. What you end up with, what the analyzer is actually looking at, is the absorption feature of specific analytes. So let's say this laser right here is measuring NO2. That NO2 at 1 ppm, these are the absorption features that we would see at 0.1. See, they're still there, but they're less. Really what it comes down to that we're at, in order to determine the concentration, looking at how much light is absorbed, in order to understand how much light is absorbed, looking at the area underneath. The larger the area underneath the peak, absorption, the higher the concentration. Looking at traditional analyzers, have the highly coherent light at a specific wavelength, so you've got a broader based energy source. You have to filter out what you don't want. You have to do some compensation. It's a more complicated analyzer. So this simplifies things because everything that we do is by absorption spectroscopy. Laser itself on the top, that's a butterfly package for a quantum cascade laser. The tunable diode laser is on the bottom. And this slide really is what it's saying is that our longevity of these are semiconductor lasers. If you're familiar with tunable diode lasers, then you understand the reliability of the lasers themselves and those analyzers. And the quantum cascade laser has those same characteristics. So what is a quantum cascade laser? It's you've got show it to you graphically in the semiconductor itself. There's a series of quantum wells. There's current. You have electrons. It goes from excited to a grounded state. That it emits a photon. The interesting thing about it, this is the quantum physics part of it that I don't have, that same electron tunnels to the next quantum well. It goes through the same transition from an excited to a grounded state, it's a photon, so on and so on. Up to anywhere from 20 to 100 times one electron will produce multiple photons. What happens when this is that the wavelength increases slightly as the up a little bit, and so we get a little bit. It's still very, very narrow, very specific, but we get a little bit of width to the window that we're looking at, so we can gather more information. So what we do, what we call it chirping, and so we apply the power stuff, electron current goes into the well, and laser wavelength frequencies. So these are the absorption peaks you see right here. Sweeps that whole package down very quickly. Now, if you remember, there's no thermal mass here at all. Very, very quickly. Very quick. So chirp about 500 nanoseconds and less than a millisecond between chirps. So we're getting very specific information. We're getting it very quick. We're getting a lot of data, and we're able to crunch those numbers and give you an update on all your concentrations every second. So the other thing is that when we chirp, we're able to sequence the lasers because we can't run different wavelengths through the same path at the same time. So the way we do multiple lasers, that chirp them in sequence. So this is CO2, NO, and CO, this one's SO2, but they go through at different times. If you notice, this is inverted, right? It is on the top, O cell is on the bottom, detector up here. But that's how we're able to do multiple measurements with one laser. With one laser. And then the laser itself looks like this. It's a kind of reminds me of an ink cartridge, and it works similarly in the sense that when you plug it in, it's aligned. So it's pre-aligned at the factory. You plug it in, it's all aligned, and it contains within itself all of the relevant information. So this plug it in, let's say in 12 years, your CO laser needs to be replaced. Pull out your old CO laser, you put this one in, power it up, and number one, it's aligned. Number two, it says to the control board, I'm a CO laser. This is designed for it. And every laser is a little bit different, so we've corrected for that so that plug this in, it's getting the correct data to make. It additionally allows you to add different measurements later on. Let's say you don't have to measure SO2 initially, but you want to measure it later. So how have we been doing with this with CEMS? Our first CEMS that we went through and passed RADA was 2017 with these. I can publicize that because we did a Cherry Point did a joint paper with them about that. It was their first one, so they did a 50-day stability test as opposed to 7 days, and really performed very well. It met or exceeded conventional analyzers. They never had to do any calibrations during that time. Our system. This is a cabinet. It's cold dry. You've got a chiller in here. And conditioning. Is your shelter to air conditioning? Depends on where you are. So we have some of these that are three-sided shelters. We have some that are on racks. Same Gulf Coast. But if you so, and then we have different capabilities. So this guy, this 19-inch rack mount, general purpose, that needs field mount. So we have a lot of these in North America, and both refining. I'd say refining is primarily where we chemical. So the typical system that you see, and this is what you normally, this is what's traditional, is you've got cold dry CEMS where you pull the sample out hot, you bring it all the way down to a chiller, and you chill it, remove the water, you get down to about 8,000 ppm, and sit down to the analyzers. And the reason why traditionally you've had to do this is that analyzers have not been able to handle temperatures, let's say 120, 120 C, that is needed to keep flue gas in vapor phase. So yeah, chill it so you can get it. So traditionally, the EPA, because that's what they're used to, they're looking for a dry basis measurement. And the difficulty is if you're looking for something that's a polar molecule, lose it in the condensate chiller. So that's a drawback. Not to mention, chillers themselves are they're a little more maintenance intensive. So what we've been doing, and I think I mentioned roughly half of all are hot wet systems. That's where we're hot all the way through the chiller, all the way through the analyzer itself, and to the plant itself. I don't know. These are PA diagrams. I just so there's no chiller, and analytes such as ammonia in particular, you're not losing everything. You're keeping everything above dew point. System. Key is that you still need to report a dry basis. So in order to do that, you have to do compensation by measuring water, calculating. So we go ahead and typically on a typical CEMS, have on our NO laser, also have a water box. We measure NO and water together, which makes it very simple. And what you need to report, there are no water standards. So it's not something you validate every time. You have to validating analytes that you're reporting. And this is working in the background. Same way that you're doing pressure and temperature compensation. So this has been very successful. So this is probably a little repetitive. This is a field mount in the Gulf Coast. It's shade. The hot wet system, it's not fairly hot. There wasn't a lot of water. So this is a kind of sample system. It's a little bit different. It's a experimental process. So it's combustion.
Is there a maximum?
So what you'll see is we for CEMS that don't have SO2, typically we want 20 like that. But as soon as you get a little bit of SO2 in there, it has 60, you have a lot of SO2 and heavy water in your. So the key there is that you have to keep every bit of the line. As soon as you get a gap, you get station. So that's one thing. But it really simplifies it. It shrinks the system, and you can get it closer to your sample point. There's a lot of advantages for it. Less real estate, less things to go wrong. If you use a sample pump, you still have maintenance on the sample pump. A lot of our customers are conductors. So you've got this jet pump pulling system, and that is a simple. You have to have good.
Why not go into situ then? As far as the extract.
Yeah, I'm not sure how we do that, but we still have to get the sample. And maybe across that we are looking at stuff. So then we've got I like the way a little bit about ammonia. Ammonia traditionally has been, ammonia slip has been traditionally done nowadays with tunable diode lasers cross stack. And the reason is to avoid the extractive system with a molecule as sticky as ammonia. So they've solved that problem, but they've created another problem, and that is they're measuring in the near infrared. Near infrared has a lot of water interference where those ammonia peaks are. So we operate in the mid infrared. That's where the quantum cascade lasers reside. Infrared has very strong primary peaks. They're strong and they're narrow, so they give us very good resolution so that we can do direct absorption spectroscopy. And so what you see right here, this is ammonia on the red, and water, 12%. So there's a lot of very, very strong ammonia peaks that we use to make measurements. We have very good low-end resolution. In the near infrared, it's actually reversed. So what you have are itty-bitty red peaks and really large water peaks. So it's a stability has been issue. So what we've done is, and it's not just us, but I know a lot of our customers who do extractive ammonia, way you make that work is you use something like silicon or tubing on the sample bundle. And I have one company, silicon or treat everything. What they get is they can get stability when they do their validations and running up to the probe and back with them. They get stability within 30 seconds. You have just stainless steel tubing, it takes several minutes. You do just silicon inert on the tubing and we get the stability. It's very doable. So you'll be able to see these changes. So we kind of solved that issue with those silicon treatments of the surfaces. And a little bit about maintenance and service. This is actually this is a hydrogen, automotive hydrogen fuel. But if you didn't have the EPA telling you to validate every day, you validate maybe once a month. There's really no parts to fail. You just go by diagnostics, make sure that everything's working fine. See the diagnostics here. Higher system configuration, laser to monitor your light path to make sure you don't have functions. And you're also looking at expected measurement. We have a FIT program that we're looking to match to make sure, because we can estimate exactly where we expect things to make sure that jive. If they don't. So maybe once a year check out, take a look at your lasers to light, see moving parts to where everything is done. You can do just about everything remotely. So you can connect with our service techs in the US as well as the factory in Scotland. And software to use to monitor, diagnose, and adjust. You can make adjustments. The good thing is when you do factory acceptance tests, you have to go to Scotland. That's a good part. So boiling this down, we get excellent resolution and high temperature operation, very, very reliable. Because, lasers are extremely stable. Absorption areas of the analytes are fixed in the laws of physics. I mean, it's physics. I would say. Moving parts within the analyzer. Calibration typically isn't needed under normal circumstances. And we are able to do a lot of measurements with one cost effective. So, been having some good success with that, and invite you to contact me if you like to talk a little bit more in detail. Anytime that you have an application, we'll take a look, bring it back past our spectroscopy. That's our booth. Come visit us. That would be good. That. Have any questions?
Dave, particular